о кристаллографии. Свен является президентом Международного союза кристаллографов в данный момент, а до того он очень много лет проработал в Союзе кристаллографии в разных качествах, в том числе занимая ключевой пост казначея и генерального секретаря. А вы понимаете, что тот, кто ведет документацию и считает деньги в каждой организации, является самым важным. Не случайно после этого он стал президентом, что он хорошо знает всю деятельность Союза изнутри. И я попросила его рассказать о современной кристаллографии, которая очень отличается от того, что было в XIX веке, и даже от того, что было в XX веке. В частности, современная кристаллография – это больше мягкая материя, чем, собственно, кристаллы. Свен, please. Да, перевода никакого не будет, не верьте объявлению в программе, вы прекрасно владеете английским языком, как вы учитесь. Если у вас возникнут вопросы, мы можем перевести видеозапись лекции, которую мы сделаем чуть позднее. Иначе вы будете слушать Свена 20 минут, а мой перевод 40. Мы решили, это очень нерациональное использование времени.
Well, thank you, Lena. It's great to be here. I will try to cover a little bit of the history and development of crystallography. I will then speak about the new possibilities that synchrotrons give to us, and depending on time, I'll give you a few examples of challenges that are soluble today that have been difficult to deal with previously. So first of all, let's see if I can work how this one works. Yeah. So crystals come in all shapes and sizes. You are surrounded by crystals in this very room, not only because it's the Department of Geology, but because all the materials that surround you that do not have an origin from the plant world are basically crystalline. So these walls on concrete, steel, typically crystalline materials. Crystals come in all shapes and sizes. On the top, you have the gypsum crystals of the Nika mine, close to Chihuahua in Mexico. More than 12 meters in length, 50 tons in weight. They have been cooked in a hot cavity above volcanic ground, being kept at 60-70 degrees C and 100% humidity for at least 100,000 years. This is a very, very slow synthesis. At the bottom is an electron micrograph of Seria, cerium oxide. The funny thing about this image, these pyramids of cerium oxide, is that this was taken by a colleague of mine in Lund, and the sample was stored for 10 years, and he found it when cleaning out his drawers and put it back into the microscope. It looks identical to what he saw 10 years ago. Seria is a very, very stable material. Now, I'm going to begin, as I said, a bit with history. Now, the title may be a little bit difficult to read at a distance, but it says a new era in chemistry. And the important thing is the publishing date, right down there, 1913. Harry Jones was a professor in California, so rather far away from Europe. What's interesting about the new era in chemistry is what it says right here. We know comparatively little about the matter in the solid state. We know the geometrical forms in which it crystallizes, and we know something about the way in which solid conduct the different forms of energy, heat, light, electricity. We know, however, very little about the internal mechanism of solids. We do not know the simplest laws to which solid matter conforms. We do not even know the molecular weights of the simplest substances in the solid state. We do not know what is the formula of sodium chloride, rock salt, or of solid water, ice. and we have no reliable means at the present of finding out these simplest matters about solids. Our ignorance of solids is nearly complete. Now this is 1913. Now let's go back in time a little bit more to the 8th of November in 1895 in the evening in Würzburg, where there is nothing good on television. Astoundingly enough, Röntgen actually had a television set, or he had a cathode tube, which is pretty much a television with very poor reception. So when you don't get it to work, you start fiddling with the controls, and that's exactly what he did. He pulled up the voltage and discovered X-rays. This was in 1895, and for that he was awarded the first Nobel Prize in Physics in 1901. In 1912, von Laue designed the experiment that was conducted by Knipping and Friedrich, and the image that you see next to his face is an X-ray diffraction pattern taken from copper sulfate. Laue was not interested in the structure of copper sulfate. He was interested in the nature of X-rays. And this experiment proved that X-rays can be seen as a form of light. They show diffraction. Of course, it also gave some idea about the typical distances in copper sulfate. But this was not Laue's intention to study, and he didn't do it either. But notice that this was 1912, the year before the American book came out saying that we have no means of studying solids. Astonishingly, the same year, Lawrence and Henry Bragg solved the structure of rock salt. 1 year before Henry Smith writes that we don't know anything about the internal mechanism of rock salt. And for that they received the Nobel Prize in 1915. Now it's rather surprising that the Braggs knew about the experiment of von Laue the same year that it was performed. And there's an interesting story behind that. It has to do with a lazy Norwegian postdoc who was working in Bragg's laboratory. His name was Hans Wegeaard, and he did the unthinkable. He took a vacation during his postdoc time, and he went to Germany. But he developed a bad conscience, so he attended a lecture when he was in Munich. He was in Munich when the results of von Laue's experiment was first made public in 1912. And so this is what he brought back from his vacation when he came back to England. The method of how to do an X-ray experiment. And of course, the Braggs, who had been looking for exactly this, a method of studying the internal mechanism of solids, immediately jumped on this idea and developed X-ray crystallography. But it's interesting to know that it was a messenger who was a postdoc who went to listen to the lecture. Now, X-ray crystallography has come of age, and it has shown us the structure of the outer core of the Earth. This is we can't do experiments on the outer core of the Earth, but we can simulate the conditions with pressure and temperature, and so find out what are the materials that are stable at these conditions. X-ray crystallography has also been used on the surface of Mars. The Mars rover had a powder X-ray diffractometer, and samples from the Mars surface were analyzed, and to the left you see the rock nest sand shadow. This is a sample taken from the surface of Mars and analyzed by the X-ray diffractometer on the Mars rover. To the right, you see a terrestrial sample of clay. This is a phyllosilicate, and what we know about the phyllosilicates on Earth is that they only form in open water. So this is a very strong indication that there was once free water on Mars. And it comes from X-ray crystallography. X-ray crystallography has made a huge impact on inorganic chemistry, organic chemistry, and material science, but it has completely transformed biochemistry. And the year 1962 is an important one because that year, Perutz Kendrew got the prize for the structure of globular proteins, studied by X-ray crystallography. The same year, Francis Crick, James Watson, and Maurice Wilkins got the Nobel Prize in Medicine or Physiology for the structure of DNA. And the image that you see at the bottom is the X-ray image taken by Rosalind Franklin, who did not share the Nobel Prize because she had been dead for 5 years when the prize was given. And it's never given posthumously. Now, proteins are large collections of atoms. And initially, the study of biomacromolecules was a very, very demanding subject. The first protein structure was that of myoglobin. It was solved in 1958, but the work that preceded it went on for a couple of decades before, and the number of person years involved is staggering. It took a few years before the next protein structure emerged. So this was 58. Then in 65, lysozyme was crystallized and solved. So the first enzyme structure. 7 years in between. So the number of examples of protein structures was very small. Still, the structure of lysozyme was one of the first that was used to model and simulate enzyme function, because it was the only protein, it was the only enzyme structure around. This, on the other hand, is a protein that appeared in the Protein Data Bank in March last year. So are these. When I was preparing this lecture, I thought I'd put in all the proteins from the Protein Data Bank entries March last year, but it turned out it took a bit of time to do that. And so I've only got about a quarter of them, and then I got tired. The interesting thing, of course, is that the number is just staggering. So there were hundreds of entries for a single month. Work that there was 7 years between the first and the second protein structure. Today, we see many, many of them appearing every month. I'll need to finish that. And so, to some extent, I would say we are all blinded by these results. And to some extent, X-ray crystallography has changed the way we think about science. I'm convinced that X-ray crystallography is the reason that science has taken certain paths and avoided others. Because X-ray crystallography gives us exquisite data on crystalline materials. And so in some way we tend to study materials that crystallize. And we avoid those that don't, because we cannot get the same information. It's a little bit like losing your car keys and then start looking for them under the street lamps because there is light, but ignoring all the stretches in between because you wouldn't find them anyway. We are, to some extent, always preoccupied with pictures. And I would like to show you just an illustration of this. I have collected 1 month of covers of Science magazine. The month of January 1880, 1910, 1940, 1970, 2000, and 2016. Just to show you what I'm thinking about. So, 1880, text. 1910, a few images. 1940, lots of images. 1970, the first color image. 2000, everything is in color. And then today, not much has changed. Interesting, the fact that we have the ability to produce color pictures means that we will do so. But it also means that the science that gets represented in high-impact journals tends to be pretty science. It tends to be science that pleases the eye as much as the mind. And I think this is another reason why X-ray crystallography has been so singularly successful, because it produces pretty pictures. That doesn't mean that it isn't useful, but it's well worth thinking about it, how we are conditioned to think in terms of pictures. Now, what X-ray crystallography does is to take an image of the unit cell of an object, the smallest repetitive unit, and then make the average of the content of all the unit cells in the crystal. So we get the content of one unit cell and we consider this to be representative of the crystal. Now we know this is not the truth. We know this is an approximation because crystals tend to be solid solutions. We can exchange sodium for potassium, and of course locally they will look different. Sodium and potassium have different sizes. They have therefore different environments, and so a unit cell with sodium will look different from a unit cell with potassium. So these are 8 French actresses from the turn of the century 1800 to 1900, all working at the Comédie Française and impersonating the Mona Lisa, La Gioconda. They're all sort of like her. Now, if you take the average of these ladies, you get something which is actually closer to the original picture. What's interesting about this process is that this is very much like a protein structure. Note the fact that you get this average picture of the face, but her hands is a dynamic region. And this is typically the sort of result that you get with X-ray crystallography. Some regions are well ordered, others less so. And as long as you're dealing with X-ray crystallography, you will get the average picture. Now, that's not a big problem because we can see, we know that Mona Lisa did not have 20 fingers on each hand. We can make the inference that these hands are moving when the picture was taken the hands were in different places in different unit cells. And therefore, we get this image which is a little bit blurry. But we recognize the Mona Lisa because it's an iconic picture. And just like the Mona Lisa, proteins have very recognizable parts, beta sheets and alpha helices, which we can recognize even if we only get parts of them. And so we can fill in the details. Very much like pictures that look a little bit like the Mona Lisa are pictures that we immediately recognize as this is the Mona Lisa, even though if they're painted by someone else, like Botero, or if they're completely out of this world, we still recognize her, because that's the way our brains work. And this is also why X-ray crystallography is so potent, because it gives us pictures, and we are really, really good at interpreting pictures. So the Braggs were working with a sealed tube X-ray source. That's something that's been around in laboratories since the early 1900s, since Röntgen discovered X-rays. So the big change that's come about when we got synchrotron radiation is that it has certain properties, and I've just listed a few of them here that I've got good examples for. The first, it's brilliant. So the amount of light that you get on a small area during a short time is a lot higher than for a sealed X-ray tube. This is a picture that you may have seen before, where the scale to the left, first of all, it's logarithmic, which is important. It's a funny unit which has to do with flux per square centimeter and solid angle and second, but it's basically flux of light. And you got the candle down here. You got an ordinary light bulb. You got old style X-ray tubes. You got the sun, staring straight into the sun. This is a second generation X-ray source that we have at my home university, and this is a fourth generation X-ray source that is it's completed and the beam lines are coming in place. This, the Max 4, is 1,000 times more brilliant than this, the Max 2, and it's 10 to the 11 times more brilliant than a conventional X-ray tube. Now, the measurement that the Braggs made of sodium chloride lasted for about a week. It took much more time for them to set up the experiment and get everything going, but it was about 1 week of exposure time, which means in 1 week we can now measure 10 to the 11 times as many crystals of rock salt. In fact, that number should be multiplied by another factor, which is even higher than 10 to the 11, which is the efficiency of detectors, which has also gone up tremendously, because they've grown in size, they've grown in speed, and they've grown in sensitivity. And what this means is that we can study very different things today than we could before, because of this enormous flux. We're not really interested in measuring rock salt 10 to the 11 times per week. And we're certainly not interested in reading 10 to the 11th papers describing the structure of rock salt. But we are interested in seeing what can be studied, because with this flux, we can look at much, much smaller crystals, and we can look at changes, things as they happen, because of the high flux. I'll give you a first example where the brilliance of a synchrotron source was important for my research, and this is a compound that sounds like it should be really simple, gold indium. Sounds like sodium chloride. It's a little bit worse. In fact, when we started working with gold indium, the structure was unknown. Looking at powder diffraction from our home source, we could see that it was rather similar to this structure, which is thallium iodide. But what's interesting about thallium iodide is the layer that I've cut out here, and which I will show you now looking at from above in this picture. But let's look at something else first. This is the diffraction pattern of gold indium at 400 degrees C as seen at the synchrotron diamond outside of Oxford. This layer of the crystal, of the diffraction pattern, is actually between the Bragg spots, and we have more or less continuous lines of diffraction that sit at 1/2 B 1/2. So this point here is 1. So this here is 1/2 30. This here is 1/2 3 1/2. So these lines are continuous along B, and they sit at 1/2, so they double A and C. Now going back to the layer that I cut out from the structure before, and looking at the shape that we can refine of the gold and indium atoms, we find that they are strangely deformed. This is not what we would expect of gold and indium. They tend to be rather spherical in crystal structures, unless there is something strange going on. What we're looking at is not the core of the atom, but the shape of the electron shell around the atom. Or rather, we are looking at the position, the dynamic position of the atom, which means if it's moving back and forth, or if it's statistically distributed over a number of positions, we would get these kinds of ellipsoids. This can equally well be represented as a structure with double positions for gold and indium. Now, the unit cell is just this piece here. So I've done a double unit cell along this direction and a bit more than one unit cell along this direction. But if we want to interpret these positions as distinct from each other so that we get this doubling that was indicated by the diffuse scattering, diffuse scattering tells us the A-axis is doubled, the the C-axis is doubled. We have no additional information along B because there the scattering is a diffuse line. There is actually just one way to interpret this pattern so that we meet these requirements, and that is by doing this. So we assume that the gold atoms are actually distributed over two sites, and that locally it behaves like this, and then it would be natural that the indium atoms move out of the way when the gold atoms move together. Now, this was at 400 degrees C. Then we took the same crystal, we can see the distances here. So the gold-gold distances here are typical bonding gold-gold distances, while this one is a bit too long, but it's also shorter than the van der Waals distance between gold. So this is a weak gold-gold bond that has formed, if this model is true. Now, we bring the temperature down from 400 to 300, and what happens is this. The diffuse scattering is replaced by sharp Bragg spots. So clearly what's going on in this crystal is that as we cool down, we find that these undecided positions now order over large patches of the crystal. This was 400 degrees C. If we now solve the structure at 300 degrees C, using the data that we have here, this is the image that we get. So clearly, the idea to split the atoms at 400 degrees C was probably a correct one. But at that temperature, we have very incomplete order and probably a lot of dynamic effects. But as we go down to 300 degrees, things start to order. We can represent this as an electron density that varies through space in a sinusoidal form. And for reasons that you will see clearly later, I've chosen to model it still by positions that are fixed. So this, of course, not really a good model of a sine wave, but I believe that these are the real positions of the atoms. And the reason that we see this sine wave is that we have very limited sizes of the crystallites on which we measure. So we have only islands of order in a sea of disorder. And this means we only see the first effects of ordering here. Then we go down to room temperature. So this was 300 degrees. Now when we go to room temperature, something interesting happens. These X-ray reflections become much stronger. They also become more numerous. You get reflections out here, which indicate that we have higher order. The intensity becomes higher, which also indicates a higher order. And if you look carefully, you can see that these sort of squares of reflections, they change shape, which means that the unit cell is changing here. Look at the old picture again. You note that they're rectangles and they're elongated in the horizontal direction. When you go down in temperature, they become elongated instead in the vertical direction. It's a very clear change of the unit cell shape. The structure looks very much the same, but the size of the ordered regions is much larger, and so the sinusoidal electronic distribution that we had is replaced very much by a square wave. And so we have a perfectly well-ordered system. So we can compare the diffraction patterns. High temperature, we only get diffuse scattering. 300 degrees C, we start getting order, and at room temperature, we have a fully ordered system. And the same thing with electron density. To the left, 300 degrees C, we have patchy order. Room temperature, we have very strict order. This is something that we got hints of when we measured at our home source, and we got good data at the synchrotron diamond. A complete difference in the quality that could be achieved. So another interesting feature is that it's monochromatic. Now, we think of X-rays that you use in the lab as monochromatic, but they're not. Neither, of course, is X-rays that you get out of a synchrotron, but they are much more monochromatic than those in the lab. So the spread of wavelengths is smaller, which means the sharpness of the diffraction pattern is much better. We also can get a closer, more collimated spot, which also helps with getting a more well-defined diffraction pattern. Always depending on that the quality of the sample is good enough, so that it's not the crystal that limits the resolution. This is something that you sometimes get very frustrated about. When you go to a synchrotron to measure a crystal more carefully, you find out that it doesn't really help to increase the quality of the beam because the quality of the crystal is crap. But I will discuss another intermetallic, copper indium, which was measured in Lund with a very high angular resolution and at a relatively large distance in order to get good resolution. We have slightly more modern X-ray tubes, but the basic principle is that. It was also measured at Diamond, and it was measured in France at Soleil. And we can look at these measurements and see what they gave us. Well, the Lund measurement looked like this. So it seems that there is some sort of extra structure to each peak here, but it's a little bit difficult to see what it is. It's not really very well resolved, because the X-ray source that we have in the home lab is not good enough. Then we measured at Diamond, and we see that we start getting a pattern here. Every reflection actually resolves into a small archipelago of reflections. This tells us that we are looking at something which is ordered on two different length scales. And finally, in France, we got these beautiful images where we can really see the reflections appearing nicely. So this is clearly a case of the good, the bad, and the ugly, where the ugly, of course, is the one we took at home. Strangely enough, though, the good and the bad are not what you think that they would be. In fact, so the ugly is ours, but the good is the Diamond data and the bad is the French data. The French data is too good to be used. It's strange, but it's true. Because what you do when you measure diffraction data is you're trying to optimize your resolution. But at the same time, you must have control of where you are in your measurement. The problem with the French data is it's so well resolved that most of the images were empty. Because these are, as I said, archipelagos of reflections in an ocean of emptiness. And they come in layers like this, and the next layer is far away. This means the normal result is you get an empty plate when you measure with very high resolution. When you have intermediate resolution, as we did for the Diamond experiment, we get enough reflections on each exposure so that we can actually maintain control of where we are in our measurement. After many frustrating attempts, I've actually given up on the French data. It's not stable enough. What this tells us, however, is, well, the copper indium system is sort of interesting. There are a number of phases here. It's a very complex phase diagram. And there's a relatively simple superstructure at high temperature, and then our more complex structure here at intermediate temperatures. And this one is not too hard to work out. We need to introduce some special tricks in indexing, but we come out with a structure where everything is nickel arsenide, so well-known mineral, and then the interstitial atoms form little patches like this, like small pieces of graphite. These are extra copper atoms that sit inside the structure. And the size here, 75 angstroms from two patches that are the same, and about 45 angstroms across a single patch. These are measures of the distance between the reflections that are closest together. But the typical repeat of a crystal structure like this is just going from the center of one hexagon to the next, and that distance equals the distance between two archipelagos of reflections. This is just a statistical picture. So this nice patch is fully occupied in the center, and right here at the edge, the probability that the atom is there is 50%. So this patch that was described in the previous picture is a statistical picture, very much like the high temperature picture of gold indium. We know something about it, but we don't know everything. For the low temperature structure, however, where we have much more information, now that was the in-house data, and this is the high resolution data, we get much better information. If we look at just one of these islands, we find that there is an enormous amount of information there, and we can actually pick out all these reflections and measure their intensities, which means we get a lot of data to determine where the atoms are. And it looks like this. So basically the same picture, patches of graphite-like nets of extra copper, but here these patches have a definite trifoil shape, and they're perfectly sharply defined. So all these atoms are really here, all the blue atoms are really there, all the red atoms are really there. So this is a fully ordered structure again. And the size is here. Well, there's 150 angstrom between the centers of two red patches. And a single patch is 100 angstroms across. So the formal unit cell of this structure is the size of a protein crystal, and it's a very simple intermetallic. You have it in your cell phones. Because lead-free solders that are used today use indium to solder copper. It's a little bit of a problem. If you live in a hot climate, which you do part of the year, these solders tend to age. And one of the most common reasons for malfunction of cell phones is the growth of whiskers of copper indium. And that's because this compound here forms over a long time, and it's very, very unwieldy. It grows as needles, and it can short out your phone. Finally, it's tunable. Now that's interesting if you want to study elements that are very close together in the periodic table, because they will give you pretty much the same, they look the same to X-rays. If they have the same number of electrons, they look the same. And I will show you a story where we were able to not only differentiate between tin and antimony, which are very close together, they're neighbors, but also to tell the story. And this is, of course, where it's nice to use high flux X-rays, because you can measure in real time and see what's going on. Anyone recognizes this? So this is the end of Hamlet, and in principle everyone is dead. Now in the beginning they're all alive, and it's not really a very interesting story if that's all you see. That's typically what you see in a chemical reaction. You have your reagents, and then at the end you have the result, and everyone is happy. But I don't think Shakespeare would have been a very famous person if that was all he wrote. So we want to see what's going on in between. And in this case, we look at stistite, my last example. So stistite is a mineral that is found at the Rio Tanamá in Puerto Rico. I've always been trying to find an excuse to go there and look for it. I haven't found it yet. It seems to be a nice place. Stistite has an absurd composition range. So it exists from 40% to 56% tin. And then there is this extra phase, which is 60% tin, 40% antimony, which only exists between 250 degrees C and 324 degrees C, and then disappears. So we synthesized stistite by by making melts with different compositions of tin and antimony and then slowly cooling them, but also by making very tin-rich melts so that we could form this high-temperature phase. And then we tried quenching it, but the thing is, it's not quenchable. We just get the same phase as we get here with some additional features, but really it's just the same phase with twinning. So the high-temperature phase is something we cannot cool down to room temperature. It transforms. So we'll look at what these phases look like, and then I'll try to explain to you what the high-temperature phase is. So, like before, we have main reflections and we have weaker reflections, extra reflections that are called satellites, that also are used as Bragg reflections to model the structure. They are actually the same in these two structures. So this is really the same structure. In this case, we just have an extra individual. There's a twin. Now, if we look at antimony itself, this is a horrible image of a bad quality X-ray experiment. So the crystal is bad, you see powder rings, and the X-ray source is bad. You see these lines that tell you that the X-ray is non-monochromatic. I was trying to give you an example of how bad things can look in the lab. This is actually an X-ray pattern that's very similar to what you saw before, only this satellite is now in the center of the rectangle. That's because antimony is basically a cubic packing of antimony atoms, but it's been deformed so that antimony layers form pairs. So this seems to be something that's close to what we see in stistite as well. If we look at stistite, we can dissolve up to 13% tin in antimony. But it looks exactly the same all the way up to 13%. Then there's a miscibility gap, and then at 34% tin, we start getting stistite, and stistite remains until we have 57% tin. And the only thing that happens is that tin breaks in between the antimony layers and forms rock salt. And the rock salt forms slabs which are 7 atomic layers thick and interleaved by pure antimony. And as we increase the amount of tin, we get less and less pure antimony until we have this structure, which is 57% tin. Then, going back to the diffraction pattern of the tin-rich stistite, so this is what was formed from high temperature and quenched. What are all these features that we see? Well, first of all, there's the stistite itself. So we have these green reflections of main reflections and satellites in stistite. There's actually a weak second-order satellite there. So these are all stistite reflections. Then you may notice that there are reflections right here and right here. Now that's tin. So stistite, when it cools down from the high temperature phase, stistite is formed, but there is too much tin, so it sweats out tin, which co-crystallizes with the stistite. Now, stistite is rhombohedral, but has almost cubic parameters, and therefore it's twinned so that we have 4 individuals along the 4 body diagonals of a cube. Tin is tetragonal, and so we have 3 individuals of tin along the 3 tetragonal axes of tin. Then there's a lot of diffuse scattering here, which tells us this is not a happy crystal. And in fact, this very sample was kept at room temperature for a month in the lab, and then we remeasured it, and there was a single crystal, single domain of stistite. So it's a very dynamic material. It self-heals with time at room temperature. Room temperature annealing. Probably not outside in Novosibirsk at this time of the year, but indoors. This is actually a very nice experiment that you should do the first time you get access to a powder machine. You should take a piece of zinc and run a powder experiment on it. Then you bang the zinc with a hammer, and you make a new powder experiment, and you will see that the powder rings are almost disappeared. They will be very broad, very disturbed. And then you wait a couple of months and you measure again on the same sample, and back are the beautiful rings, because zinc self-heals just like this material. Then we get some extra reflections here. These are because not only do we have less than monochromatic X-rays, we actually have some reflections that have twice the wavelength, and which create reflections that just do not exist. These come from impurities in the X-ray source as well. And then finally, there is real garbage as well. This is not a pure sample. So we see that we've got this item, we've got tin, and then nothing else that's really important. So we had the idea, what if we made this sample in the lab and permitted it to cool down, and then at the synchrotron reheated it? Perhaps we could get our high temperature phase back. So I tried this together with my PhD student. This was done at Soleil in France. This is the original sample, 25 degrees C. This is 300 degrees C. This is 370. Unfortunately, we don't see the twinning reflections appearing, that because we do expect that these are inherent for the high temperature phase. We do think that the high temperature phase is cubic and should have these reflections. The only thing we see is a slight change of the distance between these satellites. It gets smaller. Then, of course, the diffraction pattern gets weaker and the diffuse scattering weakens. So the only thing that happens here is a changing of the position of the satellites. Now, we know what that means. Unfortunately, that means that tin is disappearing from the structure. This scale is showing the tin content. So we start here at 25 degrees C, and then as we go up in temperature, we are changing tin content. So what's going on here is in fact this. We were trying to heat back to the high temperature phase, but instead we were just traveling along this line, losing tin all the time. Now it's 3 o'clock in the morning, and I'm willing to go to bed. But I have a very fresh and very enthusiastic PhD student, and so she convinces me that what we should do, we should open up the capillary where we have our precious single crystal. We should add a piece of solid tin on top of it. Then we should reseal it and try the experiment again with the extra tin in place to push the reaction in the other direction. Now, there are at least a handful of reasons why this cannot work. So I told her that there is at least a handful of reasons why this cannot work, and I'm going to bed. She's a very persistent young lady, so okay, we did the experiment. And strangely enough, we did not ruin the crystal. We did not ruin the capillary. It was long enough to actually snip off a piece, put in the tin, reseal, reheat. That was the plan. That was the result. We got the cubic phase. I'll never forgive her. This is the structure. It's really amazing. So what happens is, this is really rock salt. But it's delineated by single layers of pure tin. It's a little bit irregular, but basically we can look at it like this instead. It's a bit easier. So these are clusters which are sodium chloride, and they're sitting perfectly well arranged with single layers of tin in 3 dimensions like this. The only way to measure an experiment like this is at a synchrotron, because the satellites are weak, so you need the flux. The distance between satellites is small, so you need the resolution. And finally, and most importantly, the scattering difference between tin and antimony is negligible. It's 1 electron. It's 50 and 51 electrons. But this was measured at the absorption edge of antimony. And so antimony looks infinitely much heavier than tin in the experiment. It's almost a factor of 2.5. And so we were able to distinguish between them as well. Could only be done at a synchrotron. I'll finish there with a question. So does that mean that anything can be done? And yes, you can really do anything with X-rays these days. But you should be aware of the fact that there is a problem with strong X-ray sources and good detectors. Because nature has all these dirty little secrets where it doesn't behave the way we think crystals should behave. Crystals are not as well ordered and as regular as you think. Instead, they do all sorts of nasty things. And now there will be a short bestiary for you to consider, which I will go through extremely quickly. So this is an anti-malarial agent. Not a big problem here, I think. Diffraction pattern looks very nice. In one direction, there is a little bit of streaking, telling you that there is some disorder. You solve the structure, and everything is nicely described, except there are 5 relatively large residuals, electron density that hasn't been properly described. But you can see that they correspond to the positions of the heavy atoms in the structure, shifted by the same vector, all of them. This simply means that there are 2 forms of this compound. One of them is perfectly well ordered. Another one is a little bit different, and that interferes with this structure, so that we have some well-ordered layers and then one which is different, then well-ordered again and then different. Stacking faults, very common in crystals. With new X-ray methods, you can see them. This one, another drug, you cannot see the difference between these 2 forms of the crystal structure. They're actually quite different because the molecules sit at different heights. Let me demonstrate it like this. It comes in 2 forms, and red is 1/2 step up, gray is 1/2 step down. And you can see that this is clearly different from that. Here red is going like this, here red is going in a zigzag pattern. These intergrow completely randomly. But with good quality data, you can solve both these 2 structures simultaneously. This is a nice thermoelectric material. Has a very strange diffraction pattern. You can reconstruct it and see, well, there is the blue cell and the yellow cell, which are just rotated 90 degrees with respect to each other. Once you discover that, you can solve the structure nicely, and this is a nice network of antimony atoms, and there are zinc triangles, and there are single indium atoms in the channels. But this diffraction pattern contains very weak reflections encircled by the red here, and they are not explained by that twinning model. And we made another experiment where we got these reflections much stronger. Here they're among the strongest reflections there are. That's a different form of the same substance with this red cell. So there's the orthorhombic cell that we saw before. There is also a monoclinic cell. And of course, the orthorhombic cell exists in 2 orientations because of the tetragonal pseudosymmetry. The monoclinic cell exists in 4 different orientations, and they're present, both of them, and once you realize that, you can also solve this structure. Very similar to the other, but with good data you can do it. Horror story, again, thermoelectric material, zinc and timonide. This is the room temperature structure. You cool it down and you get weak extra reflections, already at 240 Kelvin. What you see is a structure that looks like this, which had very strange electron density shapes. Now, the room temperature structure is this one in red. The low temperature structure is this one in yellow. And the diffraction data that we see is clearly the combination of the two. How can that be? Well, so there we have the combination back again. So what's going on is, this is the low temperature structure, and these kite-like objects are ordered interstitials. Now, the room temperature structure is what comes in from the left here. So parts of the high temperature structure is the room temperature structure, but it also contains layers that are different. In fact, 3/4 of the structure is filled with interstitials, and 1/4 is empty, and that empty quarter is identical to the room temperature phase. So this happens by diffusion of zinc. And this intergrows with the room temperature phase because it's easy to get extra layers of the interstitial free phase up here. But just to make the story a bit more complex, if you cool further another 10 degrees Kelvin, you find that you get an even more complex pattern. At the arrows, you have the main reflections. The 3 red arrows indicate the superstructure that formed at 240 Kelvin. These blue arrows indicate what's formed at 230 Kelvin. Notice that the 240 Kelvin reflections are still there, but weaker. These two are clearly double reflections, where we have both the 4-fold and this blue, which is 13-fold superstructures present at the same time. But with good data, you can solve the structure. Although you have a hexagonal structure at room temperature, you form a triclinic 4-fold superstructure at 240 Kelvin. You form another triclinic 13-fold superstructure at 230 Kelvin. And they all live together, 12 individuals, plus the room temperature structure. And it's very similar to what you saw before. And there's the basic unit cell appearing again, with a perfect overlap. So, the future is bright, and welcome to Crystal City. Thank you for listening.
Один или два коротких вопроса. Я не услышала, что с той стороны был комментарий.
I've seen this two-dimensional population. Yes, it is two.
No, it's incommensurate. Yes.
Because you have these finite sizes of the motifs. If you look carefully, you have the impression that it was just a multiple of these hexagons of these graphite units that you have. But maybe I was wrong, so I don't know where it is getting incommensurate. Was it the quarter is mismatch?
Yes. So if I try to get that image back on.
Пока Свен ищет слайд, эту часть я переведу, потому что это касается уже не языка, а терминологии. Вы видели вот эти гексагональные трилистники цветные? И вопрос состоял в том, они чередуются периодически, и тогда это называется соразмерная модуляция, или период их чередования относится к внутреннему периоду трансляции как иррациональное число. И ответ был, что это иррациональное отношение, то есть это не соразмерная модуляция. Но это уже следующий уровень.
So in order to draw it, I have to decide on an approximant for the structure. So this is a periodic picture, and you are perfectly right. But it's only an approximation of what we measured, which is here you have the Q vectors, and they differ from any decent value. If you want to find something which is commensurate here, you need to go to a size that is probably larger than the crystal itself. These are all significant digits. So we were able to measure it with very high precision. But there is no simple superstructure that corresponds to this. The closest we get is about 180 angstroms. That would be, I guess, about a 60-fold, 59-fold superstructure, but it's just an approximation.
Рисунок выглядел периодически, потому что это движение, или то, что у нас называется аппроксимант, а вот эти вот векторы трансляции показывают, что на самом деле это иррациональное отношение, или то, что называется несоразмерным указом. Ну, кто вот у нас учится, в курсе, мы уже немного про это знаем, это особая часть кристаллографии, уже высший уровень.
And what you can see, which is quite cute, is this is also incommensurate. If you anneal at intermediate temperatures here, what you see is that this triangle here, it shrinks and it rotates. And as it shrinks and rotates, you get X-ray reflections coming out around it. So, which means there is a change in unit cell, and there is a change in the degree of order because you get higher and higher satellites. It's a very cute system. But it stops at that temperature where the lower picture was made. That's the final stage. Until you get down to 140, 150 degrees, then there is what I believe is a commensurate phase, but we have not been able to make that. The student I had who made these crystals, fantastically gifted crystal grower, a Chinese lady, she spent 2 years making these crystals. That is, she had these crystals growing for 2 years. We tried harvesting after 1 year, and they were still too poor in quality. After 2 years, they were good.
Thank you very much.
Thank you.
Спасибо.
The benefit of the students, the link to the biology and the DNA, and the question of incredibly ordered diffraction patterns versus less well ordered time effects. The DNA diffraction pattern shows from